folks, Ms. Gosling here. In this video, you're going to learn about capacitors. By the end of this video, you'll be able to solve problems involving parallel plate capacitors. So let's go ahead and get started. I'll start by talking about what a capacitor is. So up here on the left, you can see a picture of a few pictures of capacitors. They all look different, and what you might be thinking is, are you sure those are the pictures of the diodes that you showed us in class? And yes, I am sure. I can tell by looking at the capacitors here, these units, that we are in fact looking at pictures of capacitors, because this capital F here stands for the word farad, which is the unit for capacitance. But it's also important to know here, guys, that a lot of our circuit components look pretty similar in real life. One key difference between a capacitor and a diode is that our diodes have two different two different length wires, since they have a positive and a negative terminal, while our capacitors, of course, have two identical wires. However, it can be hard to tell the difference, which is why it's important to zoom in. So here we are zooming in. Over here on the right, you can see a picture of what a capacitor actually looks like. So a capacitor is something you may recognize because the basic capacitor is actually just two parallel plates, which we talked about in Unit 1 this year. However, in order to increase the capacitance of the capacitor, or basically like how much charge it can hold, we can stick something called a dielectric in between the two plates, and that's going to increase the amount of charge that can be held by a capacitor. So that brings us to the term capacitance. So capacitance, again, is going to define how much a capacitor can hold. And capacitance is going to depend on the amount of charge being held at a specific voltage. So again, capacitance is going to equal charge over voltage, and we can, and we're going to measure capacitance, as I mentioned earlier, in farads, capital F. So capacitance is measured in farads, which we are going to represent with that capital F. So now that you know what capacitance is, let's go ahead and do an example problem. A pair of parallel plates store 2.5 times 10 to the negative 6 coulombs of charge at a potential difference of 15 volts. Calculate the capacitance of this capacitor. So going through our guess method, my givens are my charge, Q, which is 2.5 times 10 to the negative 6, and my voltage, V, which is 15 volts. My unknown is, of course, the capacitance of the capacitor, which is a very silly sounding sentence now that I think about it. So our equation is nice and simple. It's the one we just learned. And that is, of course, that capacitance is equal to the charge held by the capacitor at a given voltage V. So we can go ahead and quickly sub and solve. So our capacitance for this problem is 2.5 times 10 to the negative 6 divided by 15, or 1.7 times 10 to the negative 7 farads. So you'll notice this is a very small number, and this is the kind of numbers we expect to see when we calculate capacitance. So usually when we have our capacitance, we are going to be given that measurement in microfarads. So for example, the capacitance of this capacitor is, of course, 0.17 microfarads, or 0.17 times 10 to the negative 6 farads. And I just wanted to make sure you guys were aware of this, because if you're working with capacitors in the lab, you need to be able to recognize what this symbol means. And that, again, is times 10 to the negative 6th. So Now I'd like to take a moment to talk about the energy that is stored in a capacitor. And the kind of basic equation is this first one here. Energy is equal to 1/2 QV. But we can always use, of course, C equals Q over V to simplify our equation a little bit, just kind of like how we could use V equals IR to substitute in different variables in our power equation. So for example, if I know my capacitance and my voltage, then I can say, okay, Q is equal to C times V, capacitance times voltage. And substituting that into my first equation, the energy stored in my capacitor is 1/2 times CV times V, or 1/2 CV squared. I can do the exact same thing if I'm trying to replace my voltage instead of my charge. I just wanted to make sure you guys were aware that all three of these forms of this equation they mean the same thing, and I wanted you guys to know how to derive these three forms of the equation. Now I do want to say the energy stored in a capacitor is of course electrical potential energy, similar to the energy that is stored, I suppose not quite the same as the energy stored in a battery since that's chemical potential, but it has the same ability to make a circuit run. And we're going to get into that in a later video. So I'd like for us to look specifically at a parallel plate capacitor to talk about the relationship between capacitance, area, and the distance between the plates. So say I have two parallel plates like so, and they each have an area A and are separated by a distance D. So I know from topic 10 that, from topic 10, which was in Unit 1, I know that Q over A is equal to epsilon naught, where epsilon naught is the permittivity of free space, times the voltage, that is the potential difference between the plates, divided by the distance between the plates. So again, Q is charge stored on the plate, V is voltage, but the potential difference between the plates, A is the area, and D is the separation of the plates. So what I would like to do is rearrange this. So I'm going to multiply both sides by A and divide both sides by V. So my A's on the left side will cancel and my V's on the right side will cancel. And what that will give me is that Q over V is equal to epsilon naught times A over D, or, as I know from the equation earlier in this video, capacitance for, again, parallel plates only is equal to epsilon naught times A over D. Now, I'll also note if there is something inside of my plates, if we have an insulator with a permittivity that's different than the permittivity of free space, so basically if the coefficient is different than the coefficient of free that we give for a vacuum, then we'll replace that epsilon naught with just epsilon. So C is equal to epsilon over times A over D. And if we put something inside between our parallel plates, usually what we'll be putting in is a dielectric, but there are other things that we could put between it as well. So for example, usually parallel plates on Earth will have air between them instead of a vacuum. And we'll use the coefficient for air instead of the coefficient for free space. So what I'm going to go ahead and write here, guys, I'm going to circle both of these equations because you should know both of them. And this is no dielectric, i.e. nothing between my two plates. And this is if we do have a dielectric. And I know we have not talked about dielectrics before, so let's really briefly I want to go ahead and talk about what a dielectric actually is. So a dielectric, which again is my green thing here, is something that I can put between the plates in a capacitor, and it's an insulator that becomes polarized when it's in an electric field. So it is really good at enhancing or increasing the capacitance of a capacitor. because of this property. So again, a dielectric is an insulator, so it's not conductive, but it does become polarized in an electric field, and therefore it can increase the capacitance of our capacitor, which is really nice, of our parallel plates. So on the note of increasing capacitance, I wanted to talk about, of dielectrics, I do want to talk about how we can increase capacitance. So let's look at our equation, and again, that's C is equal to epsilon or epsilon naught times A over D. So looking at the equation, if our area increases, our capacitance will increase. So this side will go up, so this side will have to go up. Similarly, if we increase our distance, the entire right side of our equation will get smaller and our capacitance will also decrease. Therefore, decreasing the distance between our plates is going to increase our capacitance. And then finally, if we can increase the permittivity of the dielectric, so if we can increase the value of our coefficient epsilon, that will also increase the capacitance of our setup. Okay, so let's look at an example of a problem where we have to think about our permittivity. So when we have a dielectric added. So in an experiment, two parallel plates with an area of 100 centimeters squared are separated by 1.5 centimeters. Calculate the capacitance of the arrangement if the gap between the plates is filled with air versus mica. So let's start by looking at air. So our givens for part A are our area, which is 100 centimeters squared or 0.01 meters squared. The distance between our plates, which is 1.5 centimeters or 0.015 meters. And we know that for air, epsilon over epsilon naught. So the permittivity divided by the permittivity of free space, or the dielectric constant, is approximately 1. Therefore, epsilon is equal to epsilon naught, our permittivity of free space. And for this question, our unknown is going to be the capacitance of this arrangement. So we're going to be using our equation. Capacitance is equal to epsilon naught times A over D. So when we substitute and solve, we are going to want to start by going to our formula packet, or the data booklet, excuse me, and looking at the list of given constants, because epsilon naught is in your data booklet, in the same place that you would find little g. And epsilon naught is equal to 8.9 times 10 to the negative 12th. And our area, of course, is 0.01, and our distance is 0.015. So when we multiply all of that out, what we'll get is that our capacitance is equal to 5.9 times 10 to the negative 12th farads. And there we go. That is our part A, our answer for part A. Let's go ahead and move on to part B. So we know that for part B, we know that, so again, looking at page 461 of my textbook, I can look up the dielectric constant for mica, and that is that epsilon, excuse me, let me change colors here, guys, and that is that epsilon over epsilon naught is equal to 5. So what that means is that epsilon is equal to 5 epsilon naught, or 5 times 8.9 times 10 to the negative 12th. Now, I have two approaches I can take here. So I can plug this all back into the equation, use this as this number here as my epsilon instead of putting an epsilon naught. Or I can recognize that capacitance, again, is equal to epsilon times A over D, and therefore is equal to 5 times epsilon naught A over D, or 5 times my answer to part A, 5.9 times 10 to the negative 12 farads. And this is what you're going to want to be able to do when you're solving these problems, is notice the relationship between your answers for part A and part B. Regardless, when I solve this out, I will get that capacitance is equal to 2.95 times 10 to the negative 11th farads. And there you go. That is my answer to this question. So let's talk takeaways. First of all, capacitors are usually pairs of parallel plates and they store charge. Capacitance measures how much charge a capacitor can hold, and that is always going to be measured at a given voltage. And finally, we know that there are many ways to increase the capacitance of a set of parallel plates, and one of those ways is adding a dielectric, or a material that is an insulator, but that gets polarized in an electric field, which is going to increase the permittivity of the space between the two parallel plates, and therefore increase the amount of charge that they can hold. So there you have it, guys. You have learned all there is to know about capacitors. Actually, you've only learned the basics of capacitors, so go ahead and continue on to the next video to learn a little bit about how capacitors behave in circuits.